In this video, we're going to concern ourselves with proving that a limit is what we say it is. And what we're going to be looking at in this case are functions of the form f of x equals ax plus b, where a is not 0. So we're going to be looking at the limit as x tends to c of ax plus b, a not equal to 0. The reason we stipulate that a not be 0 is if a is 0, then you're only looking at a constant, and, well, it's not too, those aren't very interesting. Alright, so to prove a statement of the form the limit of f of x as x tends to c is equal to L, you remember we talked about these epsilons and deltas, and basically in order for this to be true, it had to be the case that for any epsilon someone might pick, and for any x, if x is sufficiently close to delta, if the distance between, if x is sufficiently close to c, in other words, the distance between x and c is not too big, then f of x is close to L, or the distance between f of x and L is small, less than epsilon. So this part is what's known as a conditional statement. A statement of the form if P then Q is known as a conditional statement. And the favored way of proving a conditional statement is usually what's called a direct proof. And with a direct proof, what you do is you assume that P is true, and then show that Q is an immediate consequence, that Q is unavoidable. Every time you have this, every time you have P, you must also have Q. So that's how we're going to work with our limits. So let's take a look at an example. Here we're asked to evaluate the limit as x tends to 2 of 5x plus 1, and then prove that this value that we found is correct. Alright, so remember that what we want to do is start with zero is less than the absolute value of x minus c is less than delta. The less than is kind of hard to see. I apologize for that. So we'll start here and then wind up with the absolute value of f of x minus L is less than epsilon. And that has to be true for every epsilon. Alright, so that is how we are going to structure our proof. We're going to start with this statement, and then we're going to come up with a logical series of steps that leads inevitably to this statement. But the only issue here is the following. Remember that epsilon is arbitrary, and then we've got to figure out what delta is for each possible value of epsilon. So what we need is delta basically being a function of epsilon. The value of delta depends on epsilon. Well, that's not always obvious. So what we're going to do is work backwards. At least we're going to do scratch work where we work backwards. This is not an uncommon practice. If you're trying to solve a problem, sometimes you start with the goal, the end, and then figure out what could I have done to get where could I have been that led me to this, to that end statement? And so you sort of trace your way backwards. I would think that most people who write novels, for instance, they know how they want their story to end, and they set up a series of events that leads to that end. And so that's sort of the same thing. There's a working backwards. All right. So again, we're just going to be doing scratch work that leads that we can use to turn into a proof. All right. So let's get started with this. Here we have that the limit as x tends to 2 of 5x plus 1 is, let's see, that would be 11 if I'm not mistaken. All right. So what we're going to be doing is going from 0 is less than the absolute value of x minus 2 is less than delta to 5x plus 1 minus 11 is less than epsilon. All right. Now again, we're supposed to figure out a formula for delta. We need to go backwards in order to do that. So instead of starting here and going here, what we're going to do is start with this, and because the algebra will be going backwards will facilitate the algebra a little bit more than going forwards. You'll see how this is going. All right, so what we need to do is start with this and go backwards. But again, this is just scratch work. All right, so let's work with this and see if we can get it to look more like this. All right, so of course, probably you're thinking, well, I need to simplify that, and that's exactly right. Let's combine everything we can inside this set of absolute values, and so we're going to get 5x minus 10 is less than epsilon. And you're probably noticing that there's a common factor of 5. Well, we need to take out that common factor of 5. So now we've got the absolute value of 5 times x minus 2 is less than epsilon. This is promising because you've got this expression x minus 2, which you need in absolute values later. So this is working out well. Now, to go from this last step to the next step, we need to make an observation that you're going to want to use later. And that's the following about absolute values. If you've got the absolute value of a times b, that's equal to the absolute value of a times the absolute value of b. All right? So in this case, what that means is that we have the absolute value of 5 times the absolute value of x minus 2 is less than epsilon. Well, the absolute value of 5, of course, is just 5. So we have 5 times the absolute value of x minus 2 is less than epsilon. And now we can divide both sides by 5, and we get the absolute value of x minus 2 is less than epsilon over 5. This is good. This expression, epsilon over 5, that's what we'll use for delta. All right? So again, this is just the scratch work. This is the preliminary work for writing the proof. When we write the proof, what we will do is basically follow this backwards. This gives us sort of a framework on which to build the proof. So we will work our way backwards through this, filling in some details like what it is we're doing. We will flesh out the assumptions that we have to start with, and we will construct a proof for this in the next video.